Knowing the radiation levels in the immediate environment is crucial for everyone who works with or around radiation. And this is where the importance of radiation detection and measuring devices get involved. From routine monitoring to mitigating emergency situations, proper radiation detection and measuring devices can lessen or even eliminate the threats of radiation to keep individuals and even the neighboring environment safe, as these devices can provide real-time, reliable, and comprehensive information regarding low to extreme quantities of the presence of alpha, beta, gamma, X-ray, and neutron radiation. The proper understanding of the various types of detectors and knowing how each works can go a long way both for finding the best detector at a specific required task and also for enforcing the benefits of operating the specific detector. A vital part of knowing what type of detector to utilize is to know how and where it will be used, as different applications and settings necessitate different types of detectors. Radiation detection and measurement tasks are activities done in situations where there is already known presence of radioactive materials, in which this area needs to be monitored in pursuit of awareness. Awareness regarding the strength of the radioactive field, the boundaries of radioactive area, and the spread of the radioactive contamination. In these activities, there are 3 types of detectors that are commonly used. Each has its own specific recommendation based on their own strengths and weaknesses. These devices are gas-filled detectors, scintillators, and solid-state detectors.
In this video, we will tackle the first type of radiation detector and measuring device, the gas-filled detectors. Gas-filled detectors are considered to be the most commonly used radiation detector and measurement device, in which there are several types of this device. However, all of which work on the same principles. Gas-filled detectors work when gas in the detector comes in contact with radiation, and when it interacts, the gas becomes ionized that results in an electronic charge being measured by a meter. There is a common construction of gas-filled detectors based on literature. The detector has a probe, in which under its surface, there is a gas-filled chamber connected to a simple circuit. In this chamber, radiation interacts with it, then radiation will be converted into an electric pulse. The probe is also made up of thin film window that is protected by a screen to prevent breakage, scratches, and/or puncture. The anode collects the charge created through the ionization from the incident radiation. The electric circuit is then completed by using the chamber wall as a cathode. The chamber of the probe is filled with special gas that is specifically used to amplify the signal after the interaction with radiation. The amplification means that an interaction is counted but does not directly relate to the radiation dose. Looking closer, we can see that the interior chamber where the interaction will occur. The incident radiation, shown as the beta particle in the illustration, passes through the thin window of the probe and into the gas-filled chamber. The 2 charges created by the ionization continue to move towards the electrodes as the beta keeps going through the chamber. The 2 charges then strike the electrodes and a potential forms. The ionization creates an electric current in the circuit. The chamber's quenched gas stops amplification from interaction, approximately 80 microseconds, and prepares the chamber for another interaction. The electric current is processed in the scaler and sorts out the radiation interaction. Current pulses from the system current from the batteries. Inside the scaler, the signals are reported visually.
Now let's talk about the different types of gas-filled detectors. Gas-filled detectors have different types in which the major differentiating factor between them is the applied voltage across the detector, which primarily ascertains the type of response that the detector will register after the interaction with radiation. Different types of gas-filled detectors are ionization chambers, proportional counters, and Geiger-Müller tubes. Ion chamber, or also referred to as ionization chambers, are found at the lower end of the voltage scale for gas-filled detectors, as these detectors operate at a low voltage wherein they only register a measurement from the primary ions resulting from an interaction with the radioactive photon in the reaction chamber. Hence, the measurement that the detector records is directly proportional to the number of ion pairs created. With this property, ionization chambers are primarily useful in measuring absorbed dose over time. More so, they are valuable detectors for measuring high-energy gamma rays as they do not have any issue with dead time that other detector types can have. Hence, they are valuable detectors for survey meters and are widely used in laboratories to establish reference standards for calibration. On the other hand, the disadvantage of ion chambers is that they cannot identify different types of radiation, hence they are not applicable to spectroscopy, the study of absorption and emission of light and other radiation by matter. Next on the list is the proportional counters. Proportional counters or gas proportional counters are the next detectors on the voltage scale of gas field detectors. They perform similarly to an ion chamber in that interactions with radiation create ion pairs. However, they have a strong enough voltage that the ions drift towards the detector anode. As the ions approach the detector anode, the voltage increases until they reach a point where gas amplification effect occurs. Gas amplification refers to the phenomenon wherein the original ions created by the reaction with the photon of radiation causes further ionization reactions. As a result, this multiplies the strength of the output pulse measured across the detector. The resulting pulse is proportional to the number of original ion pairs formed, which correlates to the energy of the radioactive field that is interacting it. Proportional counters react differently to different energies, hence they are recommended in spectroscopy applications since they can identify the difference between various types of radiation they come into contact with. They are also highly sensitive and are highly effective at alpha and beta detection, which makes this type of detector very valuable as a contamination screening detector.
Lastly, the Geiger-Müller tubes or GM tubes are the last major class of gas-filled detectors. These detectors operate at a much higher voltage than other detector types. They differ from other detector types in that each ionizing reaction, regardless of whether it is a single particle interaction or a stronger field, causes a gas amplification effect across the entire length of the detector anode. Thus, they can only really function as simple counting devices, which are used to measure count rates or, with the correct algorithms applied, dose rates. A GM tube has to be reset to its original state after each pulse. This is accomplished by quenching, which can be done through two ways. First, this can be accomplished electronically by temporarily lowering the anode voltage on the detector after each pulse, which allows the ions to be recombined back to their inert state. Or, this can also be accomplished chemically with a quenching gas such as halogen, which absorbs the additional photons created by an ionization avalanche without becoming ionized itself. Because GM tubes undergo extensive reaction, they experience dead time with each pulse of radiation. This means that there is a lag between the pulse cascade and when the gas is able to revert to its original state and be ready to detect another pulse. That is all for the gas field detectors that are used for radiation detection and measurement. The different detectors and equipment used for radiation survey only signifies how the profession values safe and cautious practice for the welfare of the personnel, the environment, and the general public. We hope that you learned something significant from today's video. And always remember, safety awareness saves lives.